she's in the, so the Sloaney folks are the people who do the .org domain. And so when you look up a nonprofit organization, you know, you're going through Sloaney stuff. So she doesn't know anything about Postgres. She doesn't know why, you know, she doesn't know anything at all about it. It's just a data. She doesn't like Oracle. She knows that because their school district uses Oracle. But she's, so I said to her, though I had dinner last night with the people, when you do the .org, when you type in, you know, so-and-so.org. Well, it turns out she's in the charity business. And she said, oh, you mean so when you do GatesFoundation.org, that's the people it goes through? I said, yeah, I had dinner with the people that wrote that software. And she said, oh, my goodness. I said, yeah, that was a good thing. And anyway, so I'm going to start with a story. I have a friend of mine who's a project manager. This is the year 2000, so the dot-com boom is in full swing. And I have a friend of mine who's a project manager in a big telecommunications company. And he had taken over a small web application that was going to get a kind of a high profile and that they were having problems with. And it was using a commercial relational database, and they kept having problems with it. So he'd kind of made up his mind that he was going to use something like open source. And this was 2000, so Postgres wasn't that well known. And they were looking at using SleepyCat, and he was kind of entertaining using Postgres, but all he knew was that they were having problems with this database. It would crash every couple of days, and they couldn't figure out whether it was the commercial database vendor or it was the hardware, and they swapped the hardware, and bottom line was the system wasn't running consistently. So the database vendor catches wind of this, and they kind of go ballistic on him. And they come in and they say, you know, his name is Tommy. And they say, Tommy, you can't use, you have to use our database system. You can't use open source, which then in 2000 that was still, I wouldn't say that it was new, but it wasn't, there wasn't a kind of formal concept of open source in business. And he said, you know, you're going to lose all your data, and you can't extend, there's no volume manager, you can't extend anything, and blah, 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 the kind of usual FUD stuff. So Tommy's, you know, Tommy has a background in relational database, and he has in fact worked with Ingress, the academic version of Ingress, and had a strong background in relational database, and you know, he was having a problem with keeping the system stable, so his idea was that we need to start investigating other types of databases in open source. We were actually looking at SleepyCat, which is a kind of well-known key value database. And you know, he was committed to using it. So the vendor wasn't getting any traction with them. They weren't going anywhere. So what they do is they jump rank. And they go to his boss, who's the CTO of this telecommunications company. He's an old Navy guy. And his name's Jim. And they make the same argument as Jim. They say you're going to lose all your data. You can't extend the database. There's no volume manager, blah, 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 this problem, that problem. And the Navy guy, the old Navy guy, says, I have to trust Tommy. Until I have a picture of why this would fail, I have to trust Tommy's judgment. If Tommy says this is something we should use, then we have to entertain using it. So they go on and on. They say, no, you're going to lose your data. You're making a big mistake. So what this database vendor does is they jump rank a second time. And they go to the president of the company, or the president of this division of the company. And he says, they're in his office, and they say, you're going to lose all your data, that Jim and Tommy are making a mistake, you can't do volume manager, you've got to use our database system. You just have to use it. There really isn't any choice. So the president of the company looks at him, and he says, son, you know what an aircraft carrier is? And the database account rep goes, yeah, I know what an aircraft carrier is. It's a big boat. And he said, yeah, it's a big boat. He says, it's a city. He said, it's a nuclear-powered city that floats. He said, there are hundreds of people on that city. He said, do you think that a relational database system is more complicated than an aircraft carrier? And the database vendor said, no, actually, I don't know. I don't think so, no. And he said, okay. He said, do you realize that I was a captain of lost my picture of the aircraft carrier. Speaking of fault tolerant, okay, I learned a lesson about my iPad here. There we go. Okay, so I gotta get some. So he goes, do you realize that I was the captain of an aircraft carrier in the United States Navy, and that I was responsible for the lives of hundreds of men in maintaining a battle readiness, travel halfway around the world on a moment's notice? The database vendor said, no, I didn't realize that. And he said, do you know the name of my second in command on that battle carrier? I said, no, I don't know. He said, his name is Jim. It was the name of the guy that was the CTO of the company. So he said, whose judgment do you think I should trust? Should I trust your judgment or should I trust Jim's? Well, and needless to say, what happened was they trusted Jim. And they adopted Postgres, and this was 12 years ago in 2000. It was 11 and a half years ago, 2000. And that application is still in production, and many other applications that have been built since then. And that was the right decision to make. So it's kind of a lesson in how real complex systems are built. There's a level of trust involved in it. So, without any further ado, what I'm going to do is we're going to do I'm going to talk about, we're going to go through 12 years of how we've used Postgres in a carrier grade. This is it's not a single telecommunications carrier because it's been conglomerated and renamed, but it's nationwide carrier grade telecommunications that have been in existence since the year 2000 in Postgres, with Postgres, and all the way up to the present. And so let me just, before I kind of give you guys let me just talk about who I am. My name's John Scott, and I'm a software Unix database consultant. And I've been working with relational databases in Unix since 1982. And I'm a full-time consultant with them. And I'm in a company called American Messaging, which is based out of Dallas, Texas. And I'm in the Internet Engineering Group. We're responsible we sit in between the boundary of DevOps, of supporting the NOC and the operations, and new product development. So we do a lot of engineering and new product development, but also do a lot of interfacing with network operations. And I'm often a liaison between the company. We'll buy companies periodically, and I'm a liaison between the technical group and the new companies, and figuring out how to kind of put everything together. So I've been there since. I've been there since 2006. And a couple of things. In my past lives, though, I worked at Britton Lee in 1985 to 89, and actually started in 82, but I was here in Dallas. And Britton Lee is a very interesting company in the history of Postgres. They were one of the very first relational database hardware engines. And they started in Los Gatos, California. And in fact, we're in the same building that that Atari was located in. And many of the academic Ingress database developers worked for this company. And for example, Mike Olson, who's well-known with Sleepy Cat, and wrote a lot of the B-tree indexing stuff in Postgres. If you search for MAO in the source code, you supposedly can find his initials still in the comments. And I worked there for about 4 years in California, out in Silicon Valley. And then I came back to Texas, and I started a consulting partnership with some friends from Britton Lee. And we did, for 14 years, we did Unix consulting in Dallas for typical kind of boutique, high-end consulting. We would come in and do projects and large-scale kind of, it started out building Unix networks, and then it evolved into web-based type stuff as the internet got more popular. And we worked with some pretty big-name customers. Probably our best-known product that we worked on was a product called Popmail, which was a competitor to Hotmail. And they went public and then promptly folded. And then in parallel to that, we also spun off a ISP in Dallas. So I got a lot of kind of hardcore internet experience doing that. We spun a company off that was also based out of North Texas. So who's American Messaging? And why are they important, and why are they interesting in Postgres? American Messaging is what's called a wireless critical messaging and mobile provider. And they're the second largest carrier in the United States. They have 98 of the top 100%, 98 of the top 100 metropolitan areas, and we're in all 50 states. And it's a private merger of Southwestern Bell Singular and Verizon Wireless Messaging and AirTouch, which is a kind of well-known player in the paging business, or was a well-known player. Network Services, which is out of Chicago, and Graylink, and probably the most famous well-known name other than the Verizon is a company called SkyTel, which was the original BlackBerry network before they went to the cellular network. So, and SkyTel is also famous for Bernie Ebbers, who was the first of the bad boy CEOs that got thrown into jail back before Enron and back before he was the CTO of that company. So we acquired that company fairly recently. So some of our typical customers in American Messaging are mobile emergency first responders. So we have a lot of firefighters or fire departments and police stations and ambulances. We deal with a lot of hospitals, and we do also a lot of just-in-time inventory in automotive. So they have big factories, and they want to send messages out to a bunch of people out on the factory floor about who's closest to this part, things like that. And we do a lot of remote telemetry, which is turning irrigation systems on and off, air conditioning, and things like that in areas that are hard to get to with cellular. So a little bit about, I'm going to go real quick about what critical messaging is so you guys can get a feeling for kind of how big, where Postgres fits into this really big network. And we manage the physical infrastructure of. So the critical messaging is basically just paging. It's kind of the way we know about it, colloquially. And it's what kind of distinguishes critical messaging is that you normally have some kind of nationwide footprint where you have the exclusive license on a spectrum, on an RF spectrum. So, or you at least have a state-level license or some really big geographic area that you own. You have the right to broadcast on that only. And all the devices are mobile, so they're like cell. You can carry them around anywhere you want to in the country or anywhere in the footprint of the carrier. And one of the things that makes critical messaging different from text messaging is that it has a rapid one-to-many addressing. So I'm going to show you some graphs real quickly here, but it's basically you can address many things. You can address many devices with a single message and do very quick addressing. Another thing that characterizes what they call critical messaging is the devices have the capability of listening to multiple towers, so they don't lock into a single tower in the way a cell network works, where the cells are defined by frequency boundaries. So each cell has a different set of frequencies, and the phones lock into that. You don't have that technology in the critical messaging business. It's done with, they actually listen to, so you got a higher degree of redundancy. And it's very easy in the critical messaging business to crank up the power at a campus level and eliminate dead zones and things like that. It's very inexpensive to do that. So here's just a quick picture of a kind of a typical overview of the one-way satellite. We basically bounce a signal up off a satellite, and it comes back down to the towers, and then the devices are all listening simultaneously to the towers. So one tower can go out, and you still get good coverage in the area. And the devices know how to synchronize the signals from the multiple towers. So a typical kind of thing is we can send one message to a firefighter in 1 second. Like all firefighters, when fires break out in Southern California, our knock lights up, and we have a lot of firefighters are heavy smoke. Often the towers will go out in the middle of the fires, but since we're rebroadcasting with many towers, we get a much higher probability of a penetration. Another example is like a code blue in a big medical complex that's spread out. So you can't use Wi-Fi for that because we're too distributed. Also, another thing we're big in is also the irrigation systems that are located far away from cell towers. It's easy for us to set up in a relatively flat area. It's relatively easy for us to set up towers inexpensively. So here's just a kind of a graph I pulled off one of the lobbying sites. It's just showing the y-axis is time to delivery for the message, and the x-axis is the number of people you're talking to simultaneously. So if you look at, like, if you want to send a message to 100 people, same message to 100 people simultaneously, our typical rate is we're under a minute. We're actually way under a minute. It's more like about 10 seconds. But the typical on a cell coverage, and this is based on a survey that was on the cell companies, is you get a 10-minute on a cell phone because you've got to send out individual messages. If you're going across several carriers at once, of course, it comes about in half. But so you see the curve goes up as we get out into the thousands of people simultaneously. Then you're talking about 20, 30, 40-minute delays. One problem we see with the cell towers is that, like in a crisis, they'll get flooded, and then they actually shut down. They have similar kind of things like spam, equivalent to kind of spam protection. So we have a flat time on the distribution of the message. So these are the things that characterize critical messaging. And probably the last thing that characterizes is that we have a 24-hour live support. So and our support people on the phone know how to deal with emergencies all the time. So they know how to rapidly escalate up to tier 3. And a lot of times we get problems that are not our fault, but fire department's ISP will block 4444 because it doesn't know what it is, and all of a sudden they can't send their messages out, and so there's a panicky situation. You can literally hear the sirens in the background, and and the heaviness in the fire chief's voice when he says, "You better get this fixed." So our support staff knows that, kind of the way 911 support staff. They know how to escalate that. You don't get that kind of support from a cell company. Okay, so where does Postgres fit into all this? Postgres has been in continuous use with American Messaging and its ancestral companies for 12 years. And as far as I know, all of the applications that have been written in Postgres are still in production. We haven't shut a single one down. And Postgres has got a really good reputation in this company for, good ROI. It's probably the biggest thing is it's easy to maintain, and then of course there's no licensing, which is another big thing. And we also like the fact that it doesn't do a lot of weird feature creep. And so commercial vendors will give you features in the database that you don't pay for until you start using it accidentally, and then they audit you, and that's weird. And so they don't have that in Postgres, and that turns out to be that's a problem. And so they'll actually turn the feature on, and then you'll start using it, and they actually do audits, or they try to do audits. And so we don't have that issue with Postgres. I'm going to talk about three big applications that we use that are important at AMS, driven by Postgres. The first one, that was started in 2001, shortly before 9/11, is a simple message dispatching system. It's called myAirmail.com, and it's not a real complicated application. And this is the one that Tommy I was describing had switched to Postgres originally. It's not a simple application, but it was a high-profile application that the salespeople were using, so it was important for that reason. And then in 2006, we switched the interim message routing and the device configuration over to Postgres, and that was a big deal. That was a major step in the company using Postgres, and that was done in 2006. And in 2009, when we acquired SkyTel, we rewrote the event monitoring system to use Postgres for all the two-way kind of cell tower type traffic using Postgres. So I'm going to show you some stuff on that we did on that. So the first one is myAirmail.com, and it's a simple web dispatching system. Typically it's used in fire stations and nursing, as you'd see it in front of a nurse's station in a hospital. And it started with Postgres 7.1, and currently it's running 9.1. And we've been pretty good about just maintaining upgrades through it. And it was used very extensively in 9/11 because our client at the time that was doing this had a big presence in Manhattan. And when the cell towers went out, pagers still worked. And the fire departments in 2000 and the police chiefs, and even to this day to a certain degree, but in 2000 they were very geared towards using paging and emergency messaging. That was the thing to do. So that application, even though it wasn't particularly complicated, was actually a critical. So here we are. Here's the application, and it's nothing fancy about it. It's just kind of basically it's like a mail system, sort of. So you build up address books, and you send your messages out, and all this is driven with Postgres, and this has been in place since about March of 2001. And what happened was kind of interesting. We went live, I don't remember the exact time, it was in the spring of 2001 with 7.1, which was the first version of Postgres that had the write-ahead log. And so that was kind of the kicker for us that got us, okay, these guys are serious. And I had actually been to and met Tom and Bruce at an OSDN conference a year earlier and was really convinced, really sold after, we had had a good time out of the conference, and I got a really good feeling of the conference. It wasn't a real big conference, but in my opinion, it was kind of a coming out party for Postgres, and got a really good feeling for it. And so the next year, Bruce had asked me to do a talk at the OSDN in September 23rd in 2001, and I was all scheduled to do it, and had convinced management, which at that time didn't know about open source, and so they were a little leery about me just getting up there and talking about anything that we do. And I had convinced them, which took me quite a bit to do, that this was okay, and it wasn't a big deal, and we had to have it reviewed by legal and all that. And so I was all queued up to go. I think it was in Rhode Island, I believe is where it was at. But and then 9/11 happened, and as I said, paging in 9/11 was a big deal, and I put my laptop right next to my bed, and it was 24 hours for a day, 7 days a week for a long period of time. So I had to cancel the talk, and I know Bruce didn't. It was less than 2 weeks after 9/11. What were you thinking? And Bruce got a little upset at me about it. It's like, what were you? I'm like, I kept telling him we're like right in the middle of all this. Everybody was in the middle of 9/11, so probably I don't think he quite realized what I meant by the middle of it. We were like literally in the middle of it, and so like we watched the World Trade Center accounts getting created as the fire departments were building the database. They were doing all these ad hoc group systems. And it was a complete nightmare. It was just a total meltdown. Well, the good news is that Postgres the traffic just shot right up through the roof. It was just crazy. We had hospitals testing nationwide for the anthrax stuff, simultaneous testing, nationwide events. All that was going through the paging network. So Postgres came through. Oh my God, fantastic! And so just literally a couple months after we'd gone live, and it just proved itself perfectly. We had no issues at all with Postgres, and it was just a non-issue, in other words, and got a lot of kind of credit in the company after that. So here's just a little kind of profile of how the database looks like. It's got about 250,000 accounts, about 5,000 to 10,000 human beings log in. I don't know the size of the database, probably about 5 gigs, something like that. It's not a real big database. It tracks address books and aliases, and it's fairly light update traffic. And so we've been running auto vacuuming since I think it first came out, but it's not a real good test of it because it's not particularly high traffic. That's the customer profile data. So that's the critical data that you can't lose. There's a second database that handles the session cookies on every page fetch, and that gets quite a bit of traffic. And that so when you log in and you want to make sure you show the right information for the right user on the page, well, each page fetch is doing 5 or 6 queries. Originally, that was done in a Java hash table, and it would keep the session cookies in it, and kind of a typical kind of architecture. We moved it over in 8.3 we moved over the hash table to Postgres 8.3, and it actually ran faster. And one of the reasons we actually did the move was not because we were all in love with Postgres. It was just that when we were migrating to Linux, from Solaris to Linux, and we had nightmares with Java on Linux. And the hash table was originally, it was one of these distributed hash tables, just completely, most of it had to do with how the sockets got aged. But so I said, well, I can fix that. We'll just throw it in Postgres. So we migrated that over, and there's a little key value protocol that we had developed that I just spoofed the protocol and put Postgres right in front of it, and the problem went away. So we moved it over to 9.3 for the unlogged tables. We did that because if a system crashes on the session level, really all the user has to do is log back in again. So it's not a good thing, but it's not an emergency, and it's not the same kind of emergency if you lost all the account data. So we moved it over into unlogged tables, and I think it was 9.0 we turned on the auto vacuuming. We had a few issues with some of the vacuuming with the auto vacuuming with that, because the load and the update load is fairly high on that. Every time you do a page fetch, it touches a cookie that says, it re-ages the cookie and makes the cookie newer, and so we had some issues with that. Nothing real serious, but we turned on auto vacuum in 9.0. So, all right, okay. Here's just a quick picture of it. It's a typical kind of LAMP application, and there's Postgres, the accounting database. We run read writes. We do dumps, timestamp dumps, and we have a whole snapshot subsystem that the NOC knows about. And but we do point in time, snapshot dumps. We don't get any. we couldn't at the time when this was built. This is a circa 2001 architecture. We couldn't implement anything like mirroring at all. The concept really didn't exist in Postgres back then in the 7 series. So we developed a procedure, to do PG knock, which has evolved into a whole kind of subsystem that can do a PG dump with a timestamp and track that, and then rebuild live standby databases, which are the little gray guys on the right. And another thing is that one of the things you learn in the RF business is that they really know how to keep time really well. I mean, really well. And so everybody in the DevOps group, top to bottom, with just about every critical piece of equipment we deal with, has to keep the time synchronized, because that's how towers and that's how messages get delivered. If the time gets off enough of a skew, well, then you got a coverage problem, and that's why your cell phone doesn't work. And that turns out to be the whole company on the engineering side is all geared towards keeping time accurate. Well, of course, you've got really accurate time down to millisecond, and you're polling your NTP servers, and you're making sure everything's consistent and all that game. You can actually use time in the IP address as a sort of a form of a sequence number to create an order. Of course, all that fails if the time starts to get drifted off. But hey, I don't have that problem, because everybody in the company understands we've got to keep accurate time. And so what we do is we just created, since we at the time when we architected this, we didn't have anything really like real high availability. We just simply ran an application level transaction log. And since we know the point in time on the backup, we can just replay that almost immediately. And because the traffic volume is low, and because we're controlling all the queries going into it, we just replayed it. We have the software that will just replay it back. We've only had to do that once. Now, we do something similar with that when we do an upgrade, but we play the game where we know when the traffic's really low, and our upgrades are basically very, very quick. So we just play the game where the traffic's low and shut it down, flip it, and shut it back on. So we go to a snapshot that times right when we're going to do the flip, and everybody gets ready to roll the network, and boom, we just flip. All of this, by the way, sits behind load balancers. So there's VIPs all sitting between all this, which I just took out because it makes the diagram too complicated. But so we don't do anything real fancy with that. It's a working system. We have procedures in place with the knock on how to deal with a crisis. So it's not. There's a lot of things that could be improved with that, but it's not deemed important enough. Okay, so now I get into the second application. The second application was in 2006, and this was the big one. This was the one that when I first met Bruce, I teased him a little bit with. This was kind of which was the routing side, which we were also entertaining doing. And in 2001, we didn't think Postgres was solid enough to do that. But what we had been using was a lot of proprietary, custom-written stuff, and then we moved some of that over to SleepyCat. But there's in the telecommunications business, they're real comfortable with proprietary database and embedded database type systems. That's not a big deal to them. So the solution that was used then was based on SleepyCat and some custom-written code. In 2006, we decided to flip that over to Postgres, and this is absolutely critical component on the one-way messaging. This is right in the core of every message that goes in and out of the business. So we have SLAs that are tied to several seconds that are measured by hospitals that really know how to monitor data very, very well. So this was a big step for the company, was to move this over into Postgres. So the project, it started out on the one-way side, and it took many months to build the routing tables. And the way the prior network worked, the prior routes worked, was that and to a certain degree still work, was that the public phone switches, the page would go to the public phone switch that was nearest, and then the public phone switch would have an uplink to the satellite. So with the internet, prior to using Postgres, would take the inbound message, say in Dallas at the data center, and then route it back out to the PSTN in Chicago, and then the PSTN in Chicago would then shoot it over a landline to the satellite uplink, and then the message would get delivered. So you had a latency of just several seconds just in that hop, and oftentimes those links were dial-up links, and they were just all mix of types of links. these are just a very large network. So you just visualize thousands of these kind of devices in all sorts of weird environments and things like that, where these PS10 devices are located. So one of the things they wanted to do was they wanted to shorten that hop. So the message would come in, go through Postgres, go straight up to satellite. It all seems like, oh, why don't we just go out and do that and write some code and it's done? It doesn't work that way. The old analogy is you're on the highway and the car's running and you're trying to fix the engine. It's very, very true. When you have a nationwide network, you don't have a test network, right? You don't have another nation you can go to and test and simulate the scale. And you get lots of latency problems in big networks, and those are hard to simulate. And we do have little networks that we set up, like in Dallas, but it's hard to do that really properly. You really have to build a methodology for dealing with a live large network. And so it took many months for us to get that, and lots of work with Foundry load balancers and and A and Bing things. And we finally got the data moved over into Postgres. And one of the side effects of that was that we got an SQL view of the data, which was really interesting. Because prior to that, they'd been using these SleepyCat and proprietary stuff that was very difficult to see what was in the database with whatever the vendor kind of would give you dumps of the whole thing. But it's very difficult to see live data, I should say, in the database. So just a little more detail right here. This particular database tracks every customer, and when you buy a cell phone, the packets that get assembled, there's not really the equivalent of an IP transport layer. So there's a lot of knowledge in the packets about the device it's talking to. Some of that's changing, of course, with smartphones, but when this system is built in a kind of typical scenario, you actually have to do the packet construction and know that you're talking to this kind of device, it speaks on this frequency with these kind of characteristics. Well, that data is stored, and that's I can't go into too many kind of hard numbers, but that's over 1 million customers in that. And so every device that we have out in the network is configured in Postgres. All of our inbound internet traffic goes through Postgres, and that includes throttling, which is a big deal. And in the throttling, in the paging world, or in the critical messaging world, you absolutely can't black hole spam. End of discussion. Because if we misclassify it, guess what? Somebody could die. So we have to bounce the spam, all of it. All right, that's a big deal. That's not an easy problem. And and we also have to look for runaways, because we have lots of customers that will hit us too hard, which of course looks like spam sometimes in the beginning, but we'll get hit too hard with a runaway on an emergency alert because some guy's got a loop in his shell script that's refiring the same message. For some reason, NAG-IO. There's no NAG-IO people. For some reason, we get a lot of NAG-IO stuff that way. But we'll see. We have throttling so that every time message comes in, Postgres tracks a window that says, I've seen this amount of traffic in this window, and sends an error message back to the customer. So that creates an enormous amount. 70% of our SMTP traffic spam, and all of it's getting bounced, and all of them have bad DNS names, and all of them have good queue managers. So there's all sorts of this kind of crap. Whereas most rational companies would just black hole it and be done with it, which is but you can in the messaging. But we have the IT people in the hospital have to get an error message back and know, because there's a condition. We have dial-up backups. The operator will pick the phone up and page out on the phone in the middle of an emergency. So all that traffic goes through Postgres. All that throttling traffic goes through Postgres, and then we have reply. We have reply data that is we have protocols where the answer, when you reply to your email, it goes right back to the person who sent it to. Well, in the messaging business, that can get queued up in a database, and then the hospital's application will poll in batches, and so that it's not quite like email. So they'll get a batch of them back, and they'll get a commit ticket from us saying, okay, these 17 were verified as being delivered at this time, this time, this time, this time. And so it's not sent back to them the way you do it with email. Those reply data goes in. That's not a heavy, in this particular database, that wasn't a heavy volume of traffic, because most of it is one way. But some of our inter-carrier stuff was dependent on that. And then, of course, we have the engineering view of the billing records in the database goes in Postgres. So each of these are separate Postgres databases. So I'm going to flip. Okay, just a quick screen snapshot. Here's typical kind of thing that the routing tables that are stored in Postgres. So this is showing a breakdown of frequencies and things like that based on the towers. you notice that the hyperlinks are live, and one of the things I'm going to grumble about at the end of the talk is that we don't have any really good GUIs to do rapid GUI development driven from a schema. And Jim Nasby said to me, well, you got to look at something, I don't remember, in Ruby and Rails, and I said, no, but I want the data linked. I'm going to click on it, and it goes to the detail. So that means you got to know about schema. Here's just a quick profile of what the database looks like. It started out in Postgres 8.2 and all the way to 9.0. Everything runs on encrypted RAID drives. We've had a little problem with performance on that, and we're not quite sure where it's at. It was a problem. We did a little tuning on Postgres, and it kind of cleared up. But it's something that we noticed right away when we switched to encrypted drives. And these are running on pretty high-powered hardware. We had to do I forget the sync level, that everything comes back up stable, but you might lose a little bit of a window. I can't remember what that was called in Postgres, but yeah, singer's commit, right? So we had to tune that a little bit, and so we're cheating a little bit, but most important thing is the database comes back up reliably. And I'm going to show you a little bit about how we cheat on some of that and kind of keep things critical. But the main thing on the encrypted drives is, the main reason we have to use encrypted drives is for HIPAA in our auditing through HIPAA. But the encrypted drives, we have quite a bit of traffic on the encrypted drives through the throttling statistics. And Postgres handles it very well. And the vacuuming was application driven, the cron jobs doing the vacuuming. We switched that over in 9.1 to just auto vacuuming. Ran great. In fact, it ran better than but it didn't in 9.0, but it ran better in 9.1 than our application-driven stuff that knew when the database was on. It was really very, very good in 9.1. We were impressed. We didn't expect that to happen, but it was just great. And then the billing records are kept kind of and sunk into a Postgres database, and that data is flat files that get pushed over, so they don't originally go into the Postgres database. So that helps us keep the load off the database. Let me flip over and get you guys a diagram. So there we go. So here's a diagram of what we got. This is, of course, greatly simplified. But so if you notice, the only thing I've marked what's read and write and what's read only. The most important, the internet traffic comes through this upper left-hand corner. So, for example, an email message would come in. And the subscriber database is read-only, and it's snapshotted with pgdump using this system I was describing earlier. And the forward-facing servers are read-only in the database. They're not updating that database. We're able to isolate that pretty easily. The runaway and the throttle data is read-write, and actually it's not using unlogged tables, but we don't particularly care if that comes up. We don't particularly care about the history on that as long as because we can afford to lose throttling data. We have a 5-minute and then I think a 30-minute tier and if the message behaves itself properly, then the throttling will turn back off. So that kind of self-balances. If we had a crisis, as long as that database comes back up, we had a crisis and lost some of the throttling data. If that person is still active and hitting the network too hard, then it'll just rebuild the stats in the throttling database. And then the route tables are very static. They're critical, but they're very static. They change maybe every time they move towers around or they change frequency on towers, they'll retune that. But it's not something they're doing very dynamically. That's probably about a gigabyte. So that's effectively read-only from the point of view of the forward-facing services. And then we have the reply. We have the reply history when the guy on the pager replies back, and that gets multi-phase. It's not multi-phase commit, but just multi-phase writes. And each of the load balanced servers on the protocol level have a notion of a home, and so they have a home database that they talk to. And if they don't sync to the home, then there's an issue, and they need to be taken out of the load balancers. But they'll sync to the home, and then they'll replicate in times before the commit. And this is at the application logic. So before we answer the SMTP, 200 code back, it will commit to the home. If it gets an error on the commit to the home, then it will write a 500 code back to the customer. But then it does the commits to the mirrors it ignores if there's an error there, but it gets logged and alerted with SNMP, but it doesn't. The customer still sees it as being accepted. So anyway, so the final step of the read-write step is when they add a new device, we go through a call center, and the call center code was not written by us. And it's written by our IT group and our finance group. Well, it turns out, and this is one of the tricks that we got to getting the database up, getting this whole thing built quickly, is that the call center software, the provisioning software, is used to talking to thousands of terminals. And they have a notion of a nationwide device that is like a call roaming device that, in other words, you can use it anywhere in the country. And so and a lot of times it's like when you get unlimited long distance or unlimited roaming services, what they do is they program you on nationwide frequencies. And so that's how they do the roaming. And so what we did was we spoofed one of these terminals. So I took the the manual for the protocol and just sat down in Perl and started writing the protocol, just going right through it. And it's a pretty simple kind of card-oriented protocol, and it's like a circa 1970 protocol that they have thousands of these. There's tens of thousands of these terminals worldwide that speak this. And I just spoofed the protocol, and terminals are flaky, and the techs that are responsible for the tower, say, on Ohio Street, they'll cheat and they won't pull from a master database. They'll pull from a 3-day-old copy because there was a surge of the power supply. They replaced the unit. They load up a database because they forgot to do their backups that's 5 days old, and they don't tell anybody. Right? That's like, and so you lose 5 days worth of subscribers. So the billing software never trusted it. So there's statistical polling that goes through, and they do averaging, and then they do averaging forward in time and averaging backwards in time. So they literally just check and say, is that record there? Yep, it's there, and that just runs continuously on the terminals. So if something gets missing, it gets added back in again. So when I kind of saw that, I saw, well, that's how we should do the data. Instead of giving them SQL at this level, it's easier just to spoof the terminal and bootstrap the database that way. So we kind of looked like this nationwide terminal, and we started getting the feed from all these subscribers as a mirror frequency on the nationwide terminal level. And that's the billing provisioning software, because it doesn't trust anything, has its own notion of a transaction log that's just basically a text file, like in a record, and has their own infrastructure and ways of dealing with that. So, and they also have the ability to queue up the transaction. So when you're on the phone and they turn the device on, normally they'll test it over the phone, and it send a page out and you'll get it right away. And you want to do, sometimes, when you buy a cell phone, it takes like 30 minutes to activate it. Now it's gotten better, but kind of in the old days, that's because it has to get propagated through the network. Or it may be that they do the same trick we're doing, which is they'll queue up the activation of the device. So what they do is when we want to roll Postgres, we roll to one of the upgrade Postgres. We first upgrade one of the dump machines to the version N+1. We're release N+1, and then we go through the procedure in the NOC to turn off the call center provisioning, flip the VIP over to the point in time, which is synchronized right with when we're going to do the change. Remember, the transactions are queuing up here. They're not going out on the network. And then when the VIP gets reprogrammed, now we know we can't touch the old live Postgres. They turn back on the queuing system for provisioning and inflow the programming, and the device gets programmed. So, and the database gets updated. And then we go back and we switch the PG dumps get switched and master slave. So it's not real fancy, but it works. And it works because we've isolated the critical parts of the data and actually have a fairly small subset that's super critical. So this was 8.3. I'll talk a little bit about the stability of the high availability stuff. But at the time in 8.3, it wasn't even really something we could do. It just wasn't really there in 8.3. There were things in commercial, things people were selling, but it wasn't particularly there. So here's the third application. This is the one that gets me really excited. This is the one that this also had kind of a big transformational effect on our DevOps people. So when we acquired SkyTel, we acquired a large two-way network So that means it's like text messaging, basically. You send messages back and forth. It's a message-only network, so there's no voice on it. And we acquired a nationwide network, basically, that had a very primitive. I'm trying to be nice here. It had a really primitive monitoring system, and it was a primitive It was tail-f. I don't want to say that on camera. It was tail-f. And it was a lot of people watching a lot of log files with a lot of really deep knowledge. And, God bless them. And it worked. They could tell when there was hiccup. I walked into the NOC, and these guys were running 8 terminals, per seat, and running, I don't know, 30 or 40 tail-fs or 50 or 60 of them, and they just knew, when things started acting strange. I know it's kind of crazy. And so we wanted to replace that's not going to work. We got to automate stuff more. And so Postgres was going to be used in that. And essentially what we were going to look at is we were going to look at all the raw RF coming off the towers. So, and then we have what's called unified message assembly. So when you get a message coming off 6 different towers, the same pager's talking 6 different towers, there's a layer in the network that turns that into one message. And so that was going into Postgres. And then all the device registration and all sorts of kind of events that go on in the network to figure out that you're talking in this group of towers over here. And the legal made me put this in here at the bottom, but we do not log any of the message bodies. It's all HIPAA compliant. So it's the metadata associated with the message. And here's just a quick picture of what it looks like. So this is the SkyTel network. Now the engineering people made sure I put this diagram in here on the far right. The left-hand side, you have the towers connecting into our data center. That is, you have dedicated circuits, MPLS, DVDO, dial-up lines. We have all sorts of ways to talk to these towers, just kind of depending on where. And even public internet, where we'll sign an ISP up. So that flows into the data center, and the box on the right, the blue box on the right, the engineers made me put in there. That's True64, and that is not Postgres. It's running in Formix. It's a legacy system. It's very reliable, and it handles the routing and the complex traffic patterns that you see, to deliver the message in the network. It's definitely not Postgres. Not because there's anything wrong with Postgres, but it's just, it's a working system. And Formix is a great database, by the way, and it's very well tuned, and it runs. And so they made me put that in there because I thought maybe you guys would think that we're doing Postgres in the. No, we're not doing that. What we're doing is the monitoring of it. So essentially what we do is we just take raw event traffic coming off the towers, and we SQL copy it into some tables. And then simultaneously we run from the scripts that do the copying also do graph sketches of the data. And they build up, I guess, what you call streaming sketches. So they look at counts of things, and stuff like that. But then the data is going into the database, into a Postgres database. And we use Postgres mostly for really complex debugging. So let me give it just probably the best thing to get a picture. So here is that database. Here's the Informix thing I was telling you about, that Informix network. So that's a black box to us, that whole network. And then we just rsync event logs off of all these True64 boxes once a minute. Goes into the sketch servers. The sketch servers are Perl scripts crunching through a lot of data, nothing fancy at all. And they generate the ubiquitous round-robin database graphs on the right. And that's, I forgot to put in our diagram here, that's where our SNMP alerts get triggered. Some of them get triggered off that. So it's one of the cool things about the round-robin database stuff. And then the traffic itself goes into the Postgres database, which is a really big set of expensive hardware Postgres databases with lots of memory and lots of disk, and everything's really fast. And that generates the view that the field techs use and the NOC uses to see the data, more or less live within a minute, but that's live to an RF network. And so here's the kind of stuff we track. This is just a typical kind of graph. This is the devices asking to be registered, and then the blue thing says, yes, you were registered, and then the red says, no, you weren't registered. And that's just one of many types of events that we track through Postgres. And here was a kind of interesting side effect. when we got the data into Postgres, this surprised me. The guys in our DevOps group are really bright RF engineers. And these guys know how to tune RF networks, and they know how to read satellite uplinks and downlinks, and they're really smart, hardcore tech guys, but they don't know a lot about databases. So when we got the data into the Postgres database, they had a lot. The words I kept hearing was, "Oh, this is just logic," and this was like a big revelation, because for example, your home network, you don't have a Postgres view of your network. Even your little tiny RF, think about it. Your wife, how many times do you ever wonder whether somebody's somebody's stealing my bandwidth or doing something illegal on my network? You don't have a way to go back in and do a query and look at it. Okay, so what we were doing was building a nationwide view of this huge cell network in Postgres, and it was like, oh, and they were looking at the SQL scripts and going, well, that's just logic. That's easy. Anybody can do that. That's not programming was the term I heard, and that was really cool. And the telco business doesn't do that. So a typical kind of thing is I'm going to see all the RF all the radio frequency towers in Chicago with devices registering more than 10 times in the last hour. And we'll group them by zones, which is a collection of towers. And so a crane goes up right in front of a hospital, and it blocks the signal in the hospital, and all of a sudden we start getting support calls from the hospital. The crane goes back down. The field tech rolls out there. Nothing wrong with this network. Crane goes back up, That's the kind of things that we're looking for with the SQL database. So when they saw all this, it was like, it was epiphany. It was a great thing. It was a good thing, and it was a very, very enlightening for me. It was very enjoyable for me to watch, because as much as I love SQL and databases, this was a really cool thing. And of course, none of them really knew much about SQL particularly, or the history of it. So, some of them still think that Postgres invented SQL, which, I don't know how, which it didn't. And so here's a typical kind of example of a GIS type query going through Postgres. And so this is Chicago area. This is near where we're at. This is relatively live. This is shot, I think, last week. And so you see, like I can't show you some of the stuff at the top. They didn't want me to show you how we do the query and capability. Okay, I'm almost done. So here's a particular live query that we do, and you can see, and all this is going through Postgres. Okay, so I got 5 minutes here. So what happened was they all wanted to learn SQL, or sort of. I'm kind of embellishing a little bit, but SQL became an awareness. I knew they were getting somewhere when one of the engineers comes who was doing a latency calculation. He goes, "John, what's wrong? What's wrong? What's wrong?" He's thought about it. And he looks at it, and I've been selling all this stuff as set theory, and all this kind of stuff. And he looks at it, and I look at the query, and he wasn't doing a distinct and a count. So he was counting duplicate records. So it's like, Mazel tov, you're enlightened. I said, no, you got to do a count. He comes back and says, I thought these were sets. You told me these were sets. That's not a set. And I said, oh, no, absolutely, you're correct. And, what is this? These are not sets. So I thought that was kind of funny. So therefore, I had to put this slide in here. And we have Joe's books in our NOC, and they read them to a certain degree, and they like it. They like Joe's books because they're easy to read. And there's a lot of density in them, but he still keeps the language pretty light. So that was a real fun kind of. It's interesting to see how they're learning SQL. And like I said, they look at it as logic. So you just kind of logically figure the problem out, and now there's an easy step to translate that into SQL. So real quick, and I just skip through this since we're low on time. This is how we do our backup. Okay, here, real quick with where we're going in the future with Postgres. So we got 3 kind of big things on the queue that we're looking at, and one of them's encrypted paging, and that's going to be run through. All the key management gets really hard over RF networks, and so because you got the problem with the crack the primary, the communication protocol. So, and you can't use Diffie-Hellman because you got real low power requirements and you got difficult time estimates. So that's a whole new generation of pagers we're developing. So when it goes over the air, it's encrypted. You can't just put SSL into it like a smartphone because these are real low power devices. The second thing's voice over IP. And the vendor, we're doing all this outsourced to the vendor. And the vendor's all using Postgres, and they're all totally sold on Postgres. It's not Asterisk, by the way. It's a smaller company. And then the third one is we can one of the things we want to do is we want to build on-site monitoring devices for the customers using these little tiny Unix systems that are coming out. But we want to have a web interface to it and have the whole thing where they can go in and query it. So we just put this antenna and the device on the site, turn it on, give it an IP address or a Wi-Fi address, and it's done. So that's where Postgres' friendly OSS license is a real big deal. So that's what we're interested in. And I guess we have enough time. Do I have enough? We're out of time? Okay. Well, good. I can't get to the complaints I was going to have. What can I say? It works out perfect. Thank you. Thank you, Bruce. Thank you, everybody, for Postgres. I can't say enough good things about it. But